Hi, my name is Joanna Klicka, and today I'm going to be going through homework 4 Part B. Question 1 states, the process transfer function of the liquid level in the third tank of 3 tanks in series in response to changes in input flow can be described by K over tau S plus 1 cubed. Draw the block diagram for this process under feedback control with a proportional only controller with gain Kc and derive the closed loop transfer function relating the level in the third tank to the set point. Okay, so we can start out by drawing our block diagram. And as stated, that can be represented by tau S plus 1 cubed. We also know from the problem statement that this is going to be controlled by a proportional controller. Oops. Let's see if we can make a square. And that's going to have a value of Kc. At the beginning, we're going to set the height at some set point here. And then there's going to be some error between that and our actual height. That's going to be fed into the controller. On this other side, we have our output, which is just our height. And then we need a measurement device to see what our actual height value is compared to our set point. Just stop doing that. There we go. Perfect. So now we can evaluate how our height h changes with change in set point. So if we're going to write out our equation, our left-hand side is going to be h, since that's what we're evaluating. And then what goes into that is our block up here, tau S plus 1 cubed, our control gain Kc, and our error. And as I said before, our error is the difference between our set point and our actual height. And so I'm just going to go ahead and plug that in here, which is equal to K times Kc times HSP minus H all over tau S plus 1 cubed. Perfect. Now we can go ahead and identify Kc and rewrite it as the variable Gc, and K over tau S plus 1 cubed as Gp. Now I'm going to rewrite our equation with those new variables. We're going to have H is equal to Gp times Gc times HSP minus H. Now we want to isolate H on the left-hand side of the equation. So we're going to take our Gp, G3, or Gc, and multiply that through. So Gp, Gc times our set point minus Gp, Gc times our height. And we're going to move that over to the left-hand side. So we know that H plus Gp, Gc times H, which is equal to Gp, Gc times our set point. We can factor out H on the left-hand side. So we end up with H times 1 plus Gp, Gc is equal to Gp, Gc times our set point, and then divide both sides by 1 plus Gp, Gc. We end up with 1 plus Gp, Gc over Gp, Gc times our set point. Okay. Now I'm going to put our more complicated terms back in for Gp and Gc and take the Laplace of HSP. since that's our step change. And so what we end up with when we do that is in the numerator, we're going to have GP, which is K over tau S plus 1 cubed, times GC, which is KC. And then in the denominator, we're going to have 1 plus the same thing. So we have KC over tau S plus 1 cubed. And then the clause of HSP is A over S, where A is the magnitude of our step. This is all equal to H. And then we're going to simplify this a little bit more. So we're going to leave the numerator the same. So KC over tau S plus 1 cubed. That's all over. To get common denominators here in our other denominator, we're going to have tau S plus 1 cubed plus KC all over tau S plus 1 cubed times AS. This is all equal to H. And now what we can do is cancel these denominators, which leaves us with H is equal to tau S plus 1 cubed plus KC denominator, and that's times KC, also multiplied by AS. And there we have our functions. Moving on to question 2, the problem states using the, we're just going to call it RH criterion, determine the max value for KC that still yields stable closed loop behavior. So to do this, we're going to come back over to the function that we just derived, and using this criterion, what we really want to evaluate is the polynomial that we have in the denominator. Because if we can determine that all of the roots are the same sign, then we know that our system is stable. So if we expand this tau S plus 1 cubed, we end up with tau cubed S cubed plus 3 tau squared S squared plus 3 tau S plus 1 plus K times KC times S all over KC times A. This is equal to H. So now if we use the table that we know is out there to evaluate these roots, what we can write down is tau cubed 3 tau squared. This is 3 tau. And then we have 1 plus K times KC. So what we want to know is what is our next term that's going to go right here in the first column. And to solve for this, we're going to kind of do a cross multiplication, and we're going to multiply these two terms here. So we're going to have 3 tau squared times 3 tau minus these two terms right here multiplied together. So tau cubed times 1 plus K times KC. And we're going to divide that whole thing by our bottom corner term here, which is 3 tau squared. And if we simplify this, what we get is 3 tau minus 1 plus K times KC tau over 3. Really far apart. There we go. And now what we do is we take this term and we put it right here, And if we want the fourth term in the first column, we would follow the same process. This term next to it, and like our third term in the right-hand column, be 0 because these zeros technically exist here. And if we do our cross multiplication and division process like we just did, you end up with a 0. So these other terms end up being 0. And so what you end up doing is multiplying our big long term here times 1 plus k times kc. You subtract by our diagonal here, which is 3 tau squared times 0, which is 0. And you would divide by our big term here. So what you really end up with is just 1 plus k times kc. And just like before, these other terms really end up being zeros. So now if we look at our leftmost column, what we want to see is that every term there is the same sign. In this case, that means we want each term to all be positive. And this is the case for the first two terms and the last term, assuming that our k is always a positive value. But for our larger term here, with that negative sign being there, we know that there's potential for it to be negative. So what we want to do is determine what is the maximum value that kc can be before we end up with a negative value, which would cause the system to be unstable. So to do that, we take this 3 tau minus 1 plus k times kc times tau over 3, and we want to set it to greater than 0. Now we can take one term and put it on the other side, which gives us 3 tau is greater than 1 plus k times kc times tau over 3. We can cancel out the tau on each side, and we can multiply both sides by 3, which gives us that 9 is greater than or equal to 1 plus k times kc, subtract by 1 on both sides, which is 8 is greater than k times kc, and to isolate kc, we just divide by k, which leaves us with 8 divided by k is greater than k, or kc. So now we know the maximum value that kc can be is 8 over k. Finally, we can work on question 3, which states confirm the result from B2 via simulation for k equals 12 and tau equals 1.2 in response to step change increase in set point of 0.12. So over in Google Colab, I've imported our template. So to start out, we can enter the parameters given in the problem statement. So we said that k is going to be equal to 12, so that tau is equal to 1.2, and that a, our step change, is equal to 0.12. Now from parts A and B, we know we also need GP and GC for this. And so our GP was k over tau times s plus 1 cubed. Put an extra set of parentheses in there. And GC is equal to 8 over k, and then when k is 12, that's 2/3. And now we also want to make this closed loop, so we need our equation here. So this is GP times GC divided by 1 plus GC times GP. Perfect. Now for our simulation, what we want out of it is t and our HD, so our deviation variable. We have the function sim, and our inputs are a closed loop, our time domain, so we're going to say lambda t is a, that's our step change. Then we need the number of steps, so 1, 2000, and step size, I'm going to say 0.1. Now we are ready to plot, so I'm going to say fig equals make subplots, add scatter, our x is t, our y is hd, and for mode, we want lines. There we go. We can see our oscillations, and we know that we are at the max Kc value since our oscillations are all equal in size. They're not growing and they're not dying out. But to really prove that this is our max value, what we can do is go ahead and increase this Gc since it's equal to Kc. And if we just add 0.1, what we can see is that those oscillations start out pretty flat and start growing bigger and bigger. But if we really want to get a look at it, we can change our step size to 1. And this makes it very obvious. And what we can tell from this is that if we let this simulation run to infinite time, this would become unstable.